Hey, welcome back to Fat Mama Physics. In this video, we're going to go over an example that uses dielectrics in capacitors. So hopefully you already know what a dielectric is able to do. It's able to increase the capacitance of a capacitor. And effectively what we do is we change that epsilon value in when we calculate capacitance. So we'll do an example just to show you how that works. Okay, so here I have example 13, a capacitor. This is in 11.3a capacitors, topic 11. Okay, a capacitor in a vacuum has a capacitance of 6 picofarads. Okay, so picofarads meaning times 10 to the power negative 12 has been charged by a battery of EMF 12 volts. For the capacitor in the vacuum, calculate energy stored in the electric field. So this is no dielectric yet. Okay, so we know for energy stored by a capacitor, there's a couple of equations in your data booklet, and they're all based off of a derivation from a graph involving the amount of work done to move the charges across a plate, but between plates. So here we have the capacitance as well as the voltage. So the one that we're going to be using probably is going to be 1/2 CV squared. So if you don't know where that is in your data booklet, if we just open this one up, this one is going to be in topic 11, which is down here. There you go. All these ones here. It looks like the only one that they give you is 1/2 CV squared. And so just so you know, there's many different ways to calculate energy through C equals to QV. So there's many. This equation here takes on multiple forms. Just to let you know there. Okay. So conveniently, it is the one that we need. So let's do it. 1/2 C is 6 times 10 to the power negative 12. And then voltage is just 12 squared. Okay, putting that into our calculator, I get 4.32 times 10 to the power of negative 10 joules. And the answer is in picojoules, but it's 432. So moving this over twice to get you negative 12, that's going to be exactly that. So there you go. That was the first question. Not too bad. Okay, next one. The battery is removed. Okay, a dielectric with E epsilon 6 times epsilon naught is now inserted in between the plates of the capacitor. Calculate the energy stored now. Okay, so a little bit of context. If a dielectric is inserted after the battery is removed, what happens is that the electric field in the capacitor actually allows some of the charges in the dipoles and the dielectric to line up perfectly. So that actually costs a little bit of energy to do that. So in fact, the energy stored in this capacitor is going to be less than what it was before compared to 432 picojoules. Okay, so we should expect a lower number before we tackle this problem. But since the battery is removed, we know that the charge stays the same because the battery is unable to supply more charge to your capacitor. Okay, so dielectric E is equal to 6 epsilon naught, and if you're not sure what epsilon is, it is in your data booklet. It is 8.85 times 10 to the power of negative 12. Okay, so that means it's 6 times whatever that is. Calculate the energy stored now. Okay, so we can't just go and calculate the voltage and everything else. We also know that the capacitance, this is different now. And based off of our equation for capacitor, this is equal to the area times, actually it should be epsilon naught first. It's the epsilon times the area divided by distance of separation. But now since the capacitor is 6 times epsilon naught, it is 6 times greater than that, which is whatever it was before, 6 times 10 to the power of negative 12 picofarads, which is probably going to be 36 picofarads. Now that we know the C, we know the Q must be the same as before. What we can do is we can use our previous situation to calculate the charge stored on the capacitor. So before the battery was removed, there was a certain amount of charge stored in the capacitor. So we can go ahead and calculate that. Q is equal to CV, in which C was the original. C is the original capacitance, because remember, this is before the battery was removed, and then times the voltage. So if we do that, that's going to be 6 times 10 to the power negative 12 picofarads times the voltage, 12 volts. Okay, so just to make sure you know why I'm using the old capacitance is because we're trying to find the charge stored on the battery before it was removed and before the dielectric was inserted. So this is what I get for the charge. Okay, so I have the charge, I have the charge now, I have the capacitance. I can then go and use an equivalent energy equation. So we know the energy is all 1/2 CV squared. Okay, but I also know that since the voltage in a battery is just Q over C, capacitance, by rearranging that equation in your data booklet, I can then use that to substitute it in here, which is going to give me 1/2 C, and then this is going to be Q squared over C squared. So ultimately what this leaves me is it leaves me with 1/2 Q, oopsie, that's smaller, 1/2 Q squared over C. My Q is here, so that's 7.2 times 10 to the power negative 11. Square that, don't forget that, the squaring is important. And then my new capacitance, which is 6 times 6 times 10 to the power negative 12 picofarad, or farads. Okay, putting all this in, I get 7.2 times 10 to the power negative 11 joules, which is in fact just 72 picojoules. Okay, so yes, it is less than the energy we have stored before, therefore we have done correct work. Okay, so that was B. Moving on to C. All right, compare the energies in A and B. Why did the stored energy change the way that it did? Okay, well, we kind of just answered that question, because once you insert the dielectric into the electric field, what would have to happen is the electric field provided by the capacitor will cause a dielectric polarization, causing all those dipoles to line up very well with the electric field. Well, it doesn't align with the electric field, but the dipoles align so it matches the charges, or the negatives and the positives align between the dielectrics and the capacitor themselves. Kind of like this diagram here, okay? So then what happens is that, notice that the electric field provided by the capacitor is this, but then after the dielectrics align, notice is from positive to negative, it creates an internal electric field that opposes this electric field by the capacitor. So the overall electric field between the capacitor is less. And because the electric field is less, according to this uniform electric field equals to the change in voltage over D, which is the distance of separation of the capacitance plates. The decrease in the overall net electric field is going to cause an overall decrease in the potential difference across the capacitor, which then meaning that overall less energy is stored inside the capacitor itself. Okay, so D, if the battery was not removed in B, how much energy would be stored in the capacitor when the same dielectric was inserted between the plates? So in this case, the prediction is that the energy stored should be higher. Do I have to answer that later? Well, guess what? We're going to answer that later. So let's save it till E. But the expectation is the energy will be higher. I'll explain why later. Okay, so if the battery is not removed, okay, what stays the same is this voltage will stay the same. The potential difference across the battery will be exactly the same as that of the capacitor. So this is going to stay the same, okay? And this is going to be 12 volts. Capacitance is also higher than before. And we know from 1/2 CV squared, capacitance is higher. So if we have the voltage, we have the higher capacitance, we can actually just go ahead and calculate this energy. So this is 1/2 C, which is 6 times whatever it was before. You know what? I'm just going to put 36 picofarads, which is 36 times 10 to the power negative 12. And voltage is just 12 volts. And that squared is going to give us... I get 2.592 times 10 to the power negative 9 joules, which is, because it's negative 9, this is 2.59 nanojoules, okay? So yes, it is higher than before. So, ooh, do I have space here? I can use the space to explain. Perfect. Ooh, there is space. So what does that look like? If I have a capacitor, let's do this way. Okay, so I have a battery here. It's connected to a capacitor, so I'll make the capacitor look a little bigger so I can have space to draw this nice dielectric in between. So I have this dielectric inserted in between. What's gonna happen is that the battery needs to since the battery is connected, it needs to maintain the same potential drop across the capacitor as with the battery itself. But the dielectric, because it will polarize itself, it's actually going to try to draw more charges from the battery, so that it will allow the capacitor plates to have the same potential difference. Remember that the net electric field is dependent on the capacitor minus that of a dielectric. If the dielectric is inserted, yes, it would drop the overall electric field in this matter, but we know that the drop in electric field is going to affect the voltage, but the voltage cannot be affected. Because the battery is connected to the capacitor, the voltage must stay the same. Therefore, the net electric field must stay the same. This must stay the same, and since this is introduced, that means that overall, if you kind of think about it that way, the overall electric field created by the capacitor must increase. Therefore, the only way for that to happen is that more charges are being pulled from the battery. So, the number of the charges stored in the capacitor is greater. With more charges stored, the energy stored in the capacitor will also increase itself. Okay, so that is the reason why it's always better to insert a dielectric with the capacitor still connected to maximize the amount of energy stored in the capacitor. Okay, so oh well, there we go. That was the question on dielectrics. Also wanted to give a shout out to the FET simulation on this one. Really interesting and very visual, especially with the electric field line direction. So there you go. Hopefully you learned something from this video. I wish you best of luck, and Fat Mama Physics signing out.